We will continue. So, if you recall, so like we have reached the end of one aspect of approximation algorithm that we have been dealing with, right. So, if you let us just take a small this thing and let us recap what all things we did up until now. So, up until now we designed an algorithm for, if I remember, minimum spanning tree, okay, and then we moved into what I called greedy algorithms, okay. And for greedy algorithms we saw set cover both unweighted and weighted, okay. Then we saw facility location, okay, both metric as well as like just without metric, right. So, this we saw factor 2 approximation, and here we saw order ln n approximation. We also saw here what I called okay, max k coverage, right. So, this also we saw here, and for this we saw 1 minus 1 by e approximation, okay. Okay. And then we move to the generality of this, and we move to what we call sum modular function, right, sum modular functions, okay. Here first we saw what we call sum modular set cover, and in sum modular set cover we said that, okay, if my function is what integer valued, right, integer valued, right, in fact positive integer valued, okay, and monotone, right, then we gave again ln n approximation where n was max of f I, right. Okay. So, this is what we did, and then we also gave an approximation in the same setting, not same setting, but sum modular k coverage. We gave 1 minus 1 by e approximation for again monotone non negative, okay. And then we move to general sum modular maximization, okay, a general sum modular maximization, but we were talking about non negative, but we got rid of the property of being monotone, okay. And here we gave several approximation algorithm. So, we gave one approximation algorithm here. So, first we gave an algorithm using the idea of locally optimum, right, and this was 1/3 approximation, okay. And then we gave an algorithm using what we call double greedy approximation, double greedy, remember where we had this v equal to empty, like one set we had like some a or b empty set, and we made at any point of time either we decided, okay, if your element here we added here or we deleted an element from here, okay. So, this was a double greedy that gave deterministic 1/3, and but we also had a randomized version of this which gave us half approximation, and this half approximation is tight, okay. So, we have seen several such algorithms, and these are one of the most general form of algorithms that you can think of these, okay. And there are several other people study in sum modular maximization, is that now I give you this, I said, hey, imagine, so what was an input of sum modular maximization? So, input was, right, what was input was some n and a function from 2 power n to say r greater than equal to 0, and it is f, it is sum modular, right. And there were two kind of questions we could ask. We could ask output a set S mod S equal to k, and you are trying to, and f of s is like, you want to maximize f of s, right? You want to maximize f of s, the constraint is mod s should be equal to k. So, over all sets of size k you are trying to maximize, but you could also ask this question without this, like without, you can drop this constraint, okay? You could drop this constraint and just say, no, what am I, okay? You can drop this constraint and say just maximize f of s. So, these are called unconstrained, but there are several forms that people have studied after this. They said, hey, I am not interested only on this, I can also give you an n and an I, where what is n is my ground set, okay, and I is some family of subsets of n, and this ni forms a matroid, okay. So, this ni forms a matroid, and now I am not allowed to give you any set S, but a set S where what should be the constraint? S belongs to my I, S is an independent set in my matroid, and given that constraint f of s is maximized, right. So, people have studied all kind of things, there are more things than I have told you, but this is one of the most important important generalization that people have studied, right. For example, how will I get back my old algorithm for this? By taking a matroid where I is nothing but all subsets. You can prove that if I is all subsets of n, that forms a, what do you call, that forms a matroid. If I look at I and look at all subset, that forms a matroid, right. So, in that sense, this is a generalization of just normal submodular maximization, okay. But we will get to those things much more later, but all I want to tell you, the story of maximization does not end here. People have done many more things, like not why one matroid, maybe intersection of, I give you two matroids and say, hey, I am not looking for an independent set which is in this, but I am looking for independent set which is independent in two matroids. But maybe I give you not two, but I give you R matroids and say, hey, give me an independent set which is independent in each of them, right. So, I can generalize this set of questions quite a lot, and all of them have been studied based on the requirements of what kind of functions that we want to evaluate, and that requires a very different set of tools, what is called multilinear extension, convexity, so those kind of tools, which if I have a time, we will get back to the end, okay. So, that is the story that I wanted to tell you, and with that, so this is what we have done up until now, okay. Now, what we will do is we will move to a different algorithmic paradigm, which has been which is very much closer to greedy algorithm, but it has its own name, okay. So, can I rub this? Okay. So, now what I am going to do is, we are going to set up a different paradigm, okay. Okay. So, I am going to set up a different paradigm, and this paradigm is called local search, okay. So, the way the greedy is, so what is a local search paradigm? So, local search is basically at a very higher level, the idea is that you are given a problem, you are given a solution S. For a problem pi, you are given a solution S, and you define some local move, okay. You define some notion of local move, and you try to go to S star applying this local move, okay. We will see some examples of this approach, okay. So, we apply. So, basically it is an approach which starts with some solution, goes to, you keep applying this local move until you cannot, right. So, basically you can think that local moves define a ball around the solution, right. Local move provides a ball around solutions, like, and what I mean, like I say, every other solution that I can obtain from S by applying these local moves are in this ball of solutions, and I am trying to find and optimize my solution in these balls, okay. So, this is like, so now when I say, hey, no more local moves, meaning what? Like no more local moves improves, right. Then we will stop, and then we will output some S local which is optimum with respect to the local moves. Like these local moves cannot extend this algorithm any further, cannot improve the quality of my solution any further. Then I will output that. Okay? And then we will try to prove that, hey, why is the case that my local moves are not able to make these changes or improve this solution, and use that to prove certain guarantee on the approximation algorithm. Is that fine? Right? So this is a structure of all the arguments that we are going to make for next 2-3 weeks. Is we will start with an arbitrary solution, define a notion of local move, and change my solution applying these local moves. Okay? So these are very simple algorithm, and when the local move doesn't work, I will say, hey, let's output this solution, and you will see that that solution has certain qualities, and that is what we have to study. Is that fine? Okay. Okay. So the first problem in this scheme that we are going to study is like, or 2-3 problems we will study today, and let's see if we can prove something, some guarantees on them. Okay.
How is it different from greedy, because they're also trying to make the best?
I mean, I don't know whether this is exactly what I said in the beginning, right? I mean, I think they're same in my head, but like, this is also like all these algorithms are basically greedy algorithm, and I can also say local as the, but I mean, okay, that's a very bit philosophical question. I don't think I can give a very concrete answer for that. Like, okay, but at least this is how it has been termed in the literature. It's like, yeah. So in greedy, okay, so what happens is in the greedy, you never start with a solution first of all. Okay, you build your solution. Here, what I'm saying, I start with a solution and I improve its quality. So I think that could be a basic difference, right? What I'm saying, I start with a solution, but in the greedy algorithm, I never start with a solution. I build my solution, right, from scratch, right? So that could be the one difference, that here I start with an arbitrary solution or some solution and improve its quality of the solution. But in greedy, I mean, I may start with, for example, look at vertex cover. I pick up a vertex of high degree. I mean, that's a good move, but at this point of time, it is not a solution. At the end of my process, the algorithm, the solution becomes solution, right? And every time I'm making a greedy choice of what is the locally best thing that look like to build my solution. So that could be a basic difference between greedy algorithm and locals. Okay? Okay. So the first problem that I would like to study okay. So let's study max cut in undirected call. Okay. So what is my input? A graph G, and there is a weight function from EZ to R positive. Okay. And okay, and this is input, and what do I have to output? What is my goal? Output a set S subset of VG such that, I think this is how delta S is used. Yeah, delta S. What is delta S? All those U, UV is an edge, UB is in EG, U is in S, V does not belong to S. Okay. So basically, what is delta S is all this edges. Okay. Edges that are not endpoint with one here and one outside is what I call delta S. Right. UV is in edge, U is in S, V is not in S. Okay. And find output a set S subset such that delta S such that weight of delta S is maximized. And how do I define weight of delta S is basically you sum over E in delta S weight of E. This is it. Okay, is the question clear? Right? So basically I am saying given a graph G, give me a cut, give me a vertex set so that look at the edges which are going out. The weight of this set of edges is maximized. Okay? Okay. Okay. So that's the goal of my okay. Let me define some notation that will be useful for us. Okay. So some notation that we will use is whenever I write E of A comma B, I will mean edge UV, U in A, V in B. Okay. Is it fine? U A comma B, edge U in A, V in B. Okay. And of course, let's say A intersection B is phi. So basically, I am giving you some set A and B. These are the edges I will consider. This is what A B will mean. And okay, notice that for undirected graphs, okay, EAB is same as EBA. But for directed graph, what does it mean EAB? I will have to define accordingly, and we will define when we get there. Okay. So this is what, and then I will write weight of A comma B to mean just to weight of edge of A comma B, just to shortcut it. Okay. So it's basically weight of A comma B will mean weight of edges in the set A comma B. So you just take this. So this is the set of notation. Okay. Do you know any approximation for this? Have you seen any approximation algorithm for this in our course?
It's a generalization of submodular.
Is it a generalization of submodular? It's generalization or a specialization?
Specialization.
Right? So what submodular function we are trying to understand? Okay. So you are saying that and now you will see some of the ideas that are coming from here that goes into submodular maximization algorithm. So what is this? Okay. So what is this? So you are saying that I can phrase this question as submodular maximization. Am I right? Okay. Unconstrained submodular. What functions we are talking? What is my ground set, and what is the function we are talking about? What is my ground set? What is my n? And what is my function from 2 power n to r greater than 0? If I want to do submodular maximization, I have to come up with what is my n, what is my f, and show that f is a submodular function. Huh? Edges in the ground set. Okay. So for her, n seems like E of G.
We can take vertices also and then
Huh?
vertex function to be
Okay. So how many of you believe that this should be V of G? Okay. Okay. So A. Okay. So okay. So you are saying that f of s, is this the right thing? Is this a right submodular function that we are trying to optimize? What will this give? If I optimize this, what will this give me?
We are optimizing the weight, so we have to incorporate weight there.
So what is it? What should I write here? So if this is not working,
Weight of W is delta S.
okay, is this a submodular function? Cardinality I knew that it's a submodular function, but when I put these weights, is it a submodular function? right? Given this weight, I have defined this, right? So I have a weight function from edge to this. So so I have this weight function from EZ to r greater than equal to 0, and based on that I have defined this weight of delta S. Is this some modular? Okay, so let's take that as an exercise. Okay, that F is some modular. Okay, then what kind of approximation algorithm will does it imply for this? Okay, so it will imply what? Okay, so this will imply deterministic 1/3 and half. Is that fine? Right? So just by using my submodular maximization as a black box, I get this algorithm. Is that fine? Okay. So let's try to make an now handwritten algorithm. Okay, what I call handwritten algorithm using local search, and see what we are able to achieve. Okay. So what is our handmade algorithm, or what is called purpose built algorithm? Okay. So this is a procedure.
Are we expected to do better than this?
Yes, we can do much better than this. Yeah, but let's first see something. Like we will not look. This is just a randomize. So we'll try to see if we can come up with an algorithm which is not uses black box and just uses the property of max cut and come up with an algorithm. Okay. Pallavi, can you all people see red color on the board, or it is very bad?
It is fine.
Okay. Okay. So this is a procedure, undirected max cut, okay, a local search. So what does it take? It takes a graph G and the weight function e to r greater than equal to 0. So this is what it says to. Now I need to start with some solution, right? If I want to do some local search algorithm, so I initialize what? X to an arbitrary subset of Vg. Okay? Now what I will do, while there exists while following is true, what we do? So now I want to say that this is the now I need to define some local move. So what could be the local move? So suppose you have a set S here, there are two local moves. Maybe, and here is S bar, which is V minus S. What could be that maybe I have a vertex here, I move to S union V and increase the cut. That's one way. Other could be that I remove a vertex, move to S bar, and I only consider this, and I increase the cut size, right? Why? Because imagine that you have a V here, it sees 3 people here, and it sees 2 people here. Then if I move here to V, I get 3 more edges to my cut, right? I lose 2, but I gain 3. So there are these 2 possible moves that I can locally do this. So let's apply this moves. Okay. Okay. So I will say if there exists V in S, okay, such that what I should say, weight of delta of S minus V, right, is greater than or equal to weight of delta of S, then what should we do? If there is V in S, so that if I delete it, weight of edges on S minus V is strictly more than weight on this, then I should make this move, no? Right? So then I just do. S becomes S minus V. That's it. Now, otherwise, if there exists V in S bar or V minus S, okay, there exists V not in S, such that weight of delta of S plus V or S union V, whatever you want to say, is more than weight of delta S. What will I do now? S is S plus V. Okay. If none of this happens, then what happens? Else you just break is this end of the algorithm, right? So now you see I started with an arbitrary solution. I defined this is my move, right? And I've tried to, so what is my move? So it's basically exchange. If I can get my solutions, so all the solution that I can obtain by one vertex exchange is what this solution is, right? What is one vertex exchange? Either I delete a vertex from the set or I add a vertex. So this will give me a family. And what I have found a solution which is locally optimum. Is that fine? Okay. Now let's try to analyze what is the approximation for this algorithm. Okay. So now the first thing to write will be, first thing to write, why is this a local solution? Let's try to understand why is this a local solution, right? There is a reason why, okay, there is a reason why I cannot make an improvement, right? So if I draw a picture, here is my S and here is my S bar. So first thing, for all V in S, what can you say? Okay. 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 So for all V in S, can I say that weight of edges from S, let's call it little s, okay? Okay. So why I'm not? So look at this S here. Look at the edges that are coming here and look at the edges which are going out, right? So number of edges that are here, weight of the edges that are adjacent to S inside S is less compared to whatever edges that are going out, right? So this is less than equal to weight of S to S bar, right? What does S to S bar? Edges that are going to S. Ideally, I should have written S minus S, but assume there are no self loops. So what does this implies? This is this set of edges. And what is this? This is this set of edges, right? So why I cannot flip this? Because look, if I flip this, then these edges will become cut edges and these edges will become non-cut edges, but weight will increase, right? So this is perfectly fine, right? So this is one set of inequalities that we get, okay? So this is, what is other thing that we get from here? The other thing that we will get from here is that what can we say for all T in S bar, right? Why I am not able to move this to here? Because look at, there are some, because when I move here, this set of edges will go inside and this set of edges will become my new cut edges. So which implies that weight from T to S bar is less than equal to weight from S to T. Is that fine? Let's say this is what I was writing there. Tell me.
So the T's neighbors in S bar has a more weight than its neighbor in S.
That's right. Edges. What is the T S bar means edges. So this is edges that are going from T to every other vertex in S bar. Like what's I don't understand your question, Nidhi.
I thought that inequality will be reversed. That's why the vertex T is in S bar.
Yeah, no, why can't I move T to S? Look at the algorithm, right? If there exists V naught in S such that if I can add S to V and increase its weight, I will do that. Right? So I have a vertex T which is outside S. Why I am not able to add it? Because the weight of this guy to this is less than weight of this. Is that fine? Right? Okay, so now so what are we trying to estimate? Basically we are trying to understand, hey, look at the edges here and look at the edges which are inside. So which edges are not contributing to my cut? An edge which is fully contained inside S or edge which is fully contained inside S bar are not contributing to my cut. Every other edge is contributing to my cut, right? So I want to have an estimate on this. If I can say that, hey, total weight of this edges is inside the, if I can show that weight of, what is this? S to S, like edges with an endpoint in S and endpoint in S. Is that a good? Okay, okay, plus weight of S bar to S bar, like edges which are going like one endpoint in S bar, other endpoint in S bar, right? If this is, if I can show that this is less than equal to weight of edges of my graph divided by some 5, then what will this imply? So if the total weight of edges here is at most this, it means what is the weight of edges here? If I can show this inequality, what does this implies about my algorithm? So what is the weight of edges which are coming here? So the weight of edges which are coming here is weight of edges minus weight of this quantity, which is weight of EG by 5. So which implies this is at least 4 over 5 times weight of EG. But look at any cut, any max cut, its value cannot be more than weight of EG, no? Right? So which implies that, what does this imply? So this implies that this is 4 times 5 approximation, right? Because this is greater than equal to 4 times 5 of weight of opt set. Okay, let's say weight of some C where C is. Okay, so suppose C is a vertex set of G such that weight of C is opt, right? So I can say this, right? Because no, you cannot be more than the total weight of edges. So this is, so if I can show such an inequality, I'm done, right? So if I can, so we will try to show this inequality with not 5, with some other number, and then see whatever that will imply. Okay, so our whole goal is to bound the weights of edges here. Okay. Okay. So now let's try to sum all these inequalities. Okay. Why am I summing all this inequality? Because for every vertex I know locally their contribution to the cut is more than half of their total weight. Like look at the total weight of edges here. They are contributing at least half the weight of the edges which are incident on this. Right? So that is definitely happening for every vertex. Otherwise we would have moved him. Right? So what is it true about every vertex? If I look at vertex, look at its contribution to the edge cut and then look at the contribution edges. So the contributing edge is at least half of this. Yes, no? Look at any vertex and look at the edges which contributes to the cut and the edges which are not contributing to the cut. What is the weight of this? This is strictly more than weight of this. Otherwise I would have moved it. Right? So every vertex is somehow giving at least half of its contribution to every vertex, like to the cut. So now this half we should be able to get from here. Okay. So to do that, now this is just an idea. So now let's just sum these things up. So what will happen? Okay. So for all t in S bar, for all S in S, it is weight of S comma S. For all T in S bar, I want to compute weight of T to S bar, right? Is that fine? What is this? Weight of S in S. So, this is weight of this, right? This is what we were. So, if you look at this, what is this? This is basically what I called weight of S comma S. And if you look at this, what is this? This is exactly what is weight of S bar comma S bar that we want an upper bound on. Okay. But now look at, so this is what left hand side is, but this is less than equal to, each term is less by what? S to S bar, S to S bar, right? So this is summation, I can write S in S, weight of S to S bar, I should write colon. Is that fine? Wait, no? Wait, like, wait. I'm just saying this is less than equal to this. This quantity is less than equal to, so I'm using to, so this is exactly equal. This is exactly equal to this, right? But this quantity is less than some quantity, right?
There, for every edge, we are counting from both the endpoints of the edge in the.
Okay, right. Okay, so what? Okay, so you are right. We'll get there in a minute. What he's saying is right. Okay. So what he's saying that, look at this. What he's saying that, look at an edge UV. You are also counting this from U perspective as well as weight. So this should be 2 times this. This should be 2 times this. He's right. Okay. But left hand side is this, and then T in S bar. What is the other thing we wrote? Weight of S to T. What? Look at this, no? S to T. Doesn't matter, they're same. Okay.
Yeah, this will also be twice, right?
Wait. No. Please. S is in S. And S bar is here. For each vertex, I count an edge only once, no? Wait. No, I'm not talking about this. I'm just, is this correct or not at this point of time? Right? But now what is this equal to? This is exactly equal to the cut value. Okay. So this is exactly equal to weight of S bar, S to S bar. And what is this equal to? Because at this point of time they are symmetric. Okay. So this is exactly equal to 2 times weight of S bar. Okay. Now what is this? Right? What is, so now left hand side is this, right hand side is this. So 2 will get cancelled, I think. Okay. So 2 and 2 will get cancelled. Okay, let's try to understand what is. Okay, so this should be enough for us. So now let's try to understand what is this. What are these weights of these edges? Right? What is this? This is at least, right? I have to get a lower bound, right? So what is this? So this is weight of edge in G, weight of edge in G minus weight of, is that fine? Because now I am only counting edges once, right? Right? So is this fine? Right? What is the weight of this edges? Total weight of edges minus the cut edges, weight of the cut edges. So now if I get this inequality, what will I get? Right? I will get 2 times
S bar will not equal weight of S to S and
put equal.
No, but here we are using this inequality, right?
No, look,
Here we are using.
this inequality is equal to
that
this
I
quantity.
understand, but the next step here.
Yeah, so look, no, I'm just, look at the left hand side. I'm just trying to understand left hand side. Left hand side, equality, equality, equality. This is what I can write left hand side. Left hand side is equal to this quantity. Do you agree to this? I'm saying this quantity is equal to this. Is this fine or not?
Weight of S bar to S bar.
Huh?
Set S bar to S bar. It's in the second.
Okay, that's just mistake. Okay, so now I can say weight of E of G minus weight of S S bar is less than equal to weight S S bar, which is equal to weight of S S bar is at least weight of Ez by 2, and then we are done.
But won't there be a 2 there also? That is
Because there's a 2 here and a 2 here. 2 this and 2 this will get cancelled.
But in the where you started
This
the
one.
inequality, huh?
This one. What is this? It is S in S, and this is S bar.
That is same as oh, it's the opposite thing.
For this, I use this inequality.
Yes, so here since we are replacing, so since there is a 2 there, there should be a 2 there also. No, I am saying that.
From here, we use this. This is not used for this. I should write.
Okay, I understand. Sorry.
This is what it is. This is equal to this. This is less than equal to this. This is equal to this, and then this quantity I is equal to this, and I use this to get this. Okay. So what does this gives us? This gave us a deterministic factor half approximation. Is that fine? Okay. What's the running time of this algorithm? What's the running time of this algorithm? Order? Okay, have a look.
How do you find the first set S?
S is given.
Anything, put empty set. How many times this loop will work? I can keep cycling, because every time weight of cut increases by 1. So, but what in the worst case, what will be the how many number of times will it cycle here? In the worst case, huh? What? Okay, that's like, okay. So imagine okay. So you are saying that okay. So suppose you realize weight function, I give an integer and I use, so for every edge, okay, weight function is like weight of E is something like 2 power n power 1000. This is my weight, because this is only going to take how many bits? n,000, 1000 bits. So this is still polynomial time. You understand? So how much time this algorithm will take? So this algorithm could take as bad as time, according to you. Is that correct? So that is definitely, that is one bound. So whatever, so what you are saying that if m is the max of E, weight of E, then m into n square.
But can I ask a question?
Yes.
At any time I'm checking whether there is a vertex in S that I can throw out, or a vertex outside of S that I can add. So at any time inside the loop, why is the wait thing an issue. All you're doing is scanning over order and vertices.
But look how many times while loop will work.
Yes, the weights
All I'm saying that weight increases, same vertex might be added and deleted several times. Okay, so that's one kind of upper bound. What else is an upper bound? I started with some S, next I go to S1, next I go to S2. What is the property every time? Weight increases. Weight increases. Every time weight of this cut strictly increases. So what does it mean? This S, is it possible that in this loop I will get some Si which is equal to Sj? Is it possible? So what does this mean? This means every time I am encountering different sets, which means what is the total? 2 power n. Right? So there is another, but this also is very bad. Right? I mean, then in 2 power n time I can try all possible subsets now and output you the best one. So what's the point of this? Okay? So at least the way it is written, it is indeed a factor half approximation, but it is not a polytime algorithm. Okay? It is not a polytime algorithm. Okay? So we will not worry about that for now. We will do something else for now. Okay? So that, but I want you to be aware that first of all, how much time it will cycle, and there is, this is a PLS complete question. You cannot find this local search will not, like, you cannot expect to have a polytime algorithm. Okay? But we'll do that a little bit later. Okay? Okay. So at least you understand that this algorithm, as stated, can take 2 power n into polynomial in n time, as stated. Okay? So it can take okay. So the second problem of our interest will be again max cut, but in a directed graph. So let me state this problem. Okay. Okay. So now this is a max cut in directed graph. Okay. So what is my input? Input is directed graph, weight function from edges of D to r greater than equal to 0. Okay. And what is my goal? What is the goal? We have to output a set S subset of VD such that delta plus of S such that weight of delta plus of S is maximized. Now let me tell what delta plus S is and what weight is. So what is a, now we have S. Now there are some arcs which are going out and there are some arcs which are going in. Right? So delta plus of S means all those arc UV. It means there is an arc like UV, U is in S, V is not in S. Right? So I only care about the blue arcs, not the arc which is going inside. So this is why plus out arc. Okay? So I want to find a set S such that you are maximizing the weight of the blue arcs. Okay? So this is what, and weight, now once the set is defined, weight is delta plus S is nothing but summation E going in delta plus S weight of E. Right? So that is the question we are interested in, max cut in directed graphs. Okay? Can this problem also be done? Do we know any algorithm for this problem?
Can we model as unconstrained subordinate?
Can we?
know how to prove that this is submodular.
Yeah, but like as all you are saying that I can still write unconstrained submodular maximization. What is my n? N will be vertex set of D. What is my function f from 2 to the power n to r greater than equal to 0? What is this? F of x is nothing but weight of, this is what it is. Show this is submodular. Which again implies we have 1/3 deterministic and half randomized. Okay. But we will try to make an algorithm using local search. So can I, what could be the nice change here? What could be the, what can I say here? Now I just change to D. So I change to D. What should I say? What could be the potential thing? What should I say here? Huh? Right? It's a valid algorithm. Right? It's a valid algorithm, right? Now I change this, I write directed max, maximum cut, okay? Local. So this is my algorithm. Is it good enough? Will it give anything interesting? You understand my question, right? Can this lead to a constant factor approximation like half, 1/3, 1/10, 1/100, anything? What? Of course it is not polynomial time. So was the last algorithm. That's okay. I'm just saying if this algorithm, whatever running time, doesn't matter, will it give me good approximation solution? Irrespective of the running time. Let it run as much. It just gives you this kind of solution. Yes?
Yes, so do we try to do as we were doing before that, all the edges in S and all the edges in S bar, this solution?
Yeah, that's okay. That's a proof strategy. But first of all, before even go proof strategy, is this algorithm, do you think it will give a good approximation? Or you can come with a family of examples where it will fail? Let's look at the following directed graph. You had some questions, Sushmita. Okay. So here I have n by 4 vertices, and here I have another n by 4 vertices. Okay, and the arcs are like this. Okay, and here I have n by 2 vertices. And how are my arcs? Okay, and all the arcs, like imagine that all the arcs are going here. Like this is like a, among here, it is k n by 4 times n by 2. Like it's a complete arc. All there's between any vertex here u and v, there's an arc, but v to u. Okay, and suppose I call this initially S, I start with this S. What happens then? Initialize S to an arbitrary set of Vg. If I initialize S to this, what happens? Can I make any move?
These n by 2 vertices don't have any connection with that.
No, they're just like that. Can I make any move? Right? Can I delete any vertex from here? Can I move any vertex from here? If I move to this, my cut size will decrease. Okay. Can I move any vertex from here? If I move here, what happens? Cut size will not increase at least. If I move here, cut size is not going to increase. So there is no move happens. But if I took this guy in one side, n by 2, and I put this n by 4 guy, like let's call it x, y. I put y in the one side and s on the x. Now you tell me how many edges are going out. It's like roughly n by 2 times n by 4.
What is your starting one in this case?
S.
No, why?
Y is in the left side. Suppose I return the set y as my algorithm. How many arcs are going out of y? N by 4. Okay, right? Is it okay? Look, this is my graph. Imagine that I initialize S to S. Can I make any move? Then if I output this S, what is the total number of out arc going? N by 4. Okay. But if I would have output Y, what is the total number of arcs that I will output? At least n by 2 cross n by 4. Output Y, all the out arcs that are going. Whatever, like I initialize S to an arbitrary set of VG. So I can start with this S itself. Right? I've never said that. I mean, I'm sure I can show an example where you start with, like, of course I can't start with Y. If I start with Y, then I'm done. Right? Then probably I will be done. You understand what I'm saying? If I start with Y, then I'm done. But like, of course, I'm saying that because algorithm allows me to start with any S, let me start with, right? And for example, if I started with empty, for a long time, I may be adding these vertices first, right? Because each of them do give me a movement, do give me an increment. I start with empty set, and each time first I add this. Once I get this vertices, then I will stuck, right? But so what does this imply? That at least as stated, this algorithm gives nothing. As stated, this algorithm gives nothing, which is nothing. Like, yeah. So like approximation factor is a function of n, right? I return some n by 4, but actually the best can be n square, right? Okay. So rather than I just keep everything, I will say, hey, let's not return just S, okay? I will say return S or S bar, whichever has max weight. You understand? I did nothing to my algorithm. I'm constructing S. I said, okay, is S good or S bar good? Which has a better out arc? Whichever it is, let me output that. So if I don't do this twist, we are dead. And if we do this twist, we will prove that it is perfectly fine. Do you remember this twist? Where we did this twist? When we were doing submodular maximization, local optimum, what we did, either this set or its complement. This is exactly that move. So it comes, so why people thought about that? Because people can try to these concrete things and they see how things work. Is that fine? Okay. So now we will try to analyze this algorithm in the remaining class. Okay? So you understood that we need this twist. Without this twist, it is not going to work. Okay. So whenever you are doing some of these things, the best way to analyze is to draw these sets. So algorithm outputs what? So let's draw these boxes. So what is this? S, and this is S bar. Okay. Now suppose O is my optimum set, or okay. So what is my O? O is optimum, right? This is a set which goes. So how will O? So let's think that this is how O and O bar is. Okay. So O will take some elements of S and some elements of S bar. O bar will take some elements here, some elements here. Okay? Okay. Okay. So now, so what is, if I look at E, O, O bar, this is, weight of this is an optimum set, right? What is E of O? All the arcs that are going from O to O bar. And now when I write O to O bar, all, here I mean these kind of arcs. This is in O and this is in O bar. Okay? So now what I want to do? I want to understand how this and max of weight of E of S comma S bar and okay, and weight of E of S bar comma S are related to each other. This is what I want to understand, right? This is what my whole goal is, that I want to understand how this and how max of these two are related, because what I am outputting, I output S or S bar, whichever gives me the maximum weight, right? Is that fine? If you are confused, ask now, because analysis will become more messy if you do not understand till here. Any question? Okay. Now let us try to understand how edges of O and O prime will look like. Okay. Okay. Sometimes I use comma, sometimes I use column. Forgive me for this. Okay. This is not S bar.
Hi Saket.
Yes.
Can you repeat what are the two quantities that you are trying to relate?
Look at the edges. O is an optimum set, right? So I want to understand weight of edges which are leaving O, that is E O O bar, right? And I want to understand what is the weight of E O O bar. Okay. And I either return the set S or I return S bar, right? Whichever is the maximum weight. Is that fine?
Yeah.
So now I want to relate weight of edges that are emanating out of O to maximum of edges emanating out of S or edges emanating out of S bar. Out arcs, not.
I didn't get this.
What is the algorithm returning? Algorithm either returns an S or either returns an S bar, right? Whichever is the maximum, right? And what do you mean maximum? It just counts all the outer arcs leaving S bar, or it counts all the outer arcs that leaving S, and whichever is a larger weight, it returns that. That's what the algorithm does. So now what I have to relate? I have to relate how is the optimum weight and algorithm's return weight are related to each other.
Okay.
Okay, and what is the algorithm's weight? It is either maximum of what? Either weight of edges leaving, like edges with tail in S, head in S bar, or edges with head in S bar and tail in S bar and head in S.
Okay, got it.
Okay. Okay, so let's try to understand what we can. So what we can say about this. Okay. So now let's try to understand how. So what are we? So like look at the edges from O to O bar. Okay. How are the edges going? Okay. Either I start from a vertex here, I go to this edge. Either I start from vertex in here and I go. I am trying to understand only O and O bar. Either I start a vertex here and I go here, or either I go here. Is that fine? These are the four kind of arcs that leave O and go to O bar. Is that fine with everybody? Right? So let's try to understand each of these classes of arcs. So I can write E of O bar is equal to, there are four disjoint kind of arcs. O intersection edges from O intersection S to O and this is, so blue side is S, and this is S, this is S bar, and this is O, and this is O bar. So what is this? O intersection S to what is this? O bar intersection S. This is one kind of arcs, and this is you can do disjoint union with. Okay, now let's try to understand this. So this to this and this to this. So what is the other kind of arch? E of O intersection S to O bar intersection S bar. Is that fine? Okay. What is the third kind of edges? What is the third kind of edges? What is the third kind of edges? Is here. What is that? E of O intersection S bar to here. What is that? O bar intersection S. Disjoint union E of this to this, right? So O bar intersection S bar. What is the last one? O bar intersection S bar. So these are the four kinds of edges. Okay. Imagine that if I can show that each of these quantity, each of these four quantity, let's say this is 1, this is 2, this is 3, and this is 4. Okay. So if I can show that each 1 is less than equal to weight of S comma S bar, or rather if I say that 1 is less than equal to max of weight of S comma S bar, weight of S bar comma S. If I show 1 is less than equal to this, 2 is less than equal to this, 3 is less than equal to this, 4 is less than equal to this, then what can we say? I saw that each of these quantity is at most max of this. Then what will I get? Then what will we get? Then we can say that weight of O bar is less than equal to 4 times max of this quantity, right? So let's, without loss of generality, let's assume without loss of generality, what are we going to assume? That let's say, just for it will not matter, that weight of S to S bar is greater than equal to weight of S bar to S. Like it doesn't matter, right? Whichever it is maximum. So then what will imply? So it is this will imply, so then in this case you will return what? S, right? If this happens, then you will return S, right? So then if I can, this will imply 4 times weight of S to S bar, and then you have approximation, right? Then this is what you're returning. This weight is at least 4 times this, and then you are happy. Is that okay? Okay. So now let's go about and try to prove each of these inequality, and then we will be done. Okay. Okay. So let's see which all inequalities are easy. Okay. So let's see which all inequalities are obvious, okay, and which all inequalities are not obvious. Okay. So let's try to understand one inequality. Okay. Okay. Let's see. Look at this. Look at this. Which term is this? I am not saying. Look at this set of arcs. What are these kind of arcs? What are these kind of arcs?
S to S bar.
This is where it is
Subset
written.
of S to S.
No. So what?
O intersection S to O bar intersection.
This is O intersection S to O bar intersection S bar. Look at this. What can you say about this? Look at this S to S bar. Like all these arcs are also from S to S bar arcs, no? Because they are starting in S going to S bar, right? There are many more arcs here actually. But all the arcs that go from O intersection S to O bar intersection S bar is also an arc for S to S bar. Is that fine? Right. So this is definitely, I can show that this is less than equal to, okay. So from here we can show at least this because of this green, right? So what we can show is the following. So if I have to write formally, let's write it formally, is that weight of O intersection S to O bar intersection S bar is less than equal to What I can say, O intersection S is less
Weight of S to S bar.
is less than equal to,
S to S bar.
okay, no, 1 second, sir. O intersection S to S bar, because I'm only increased. O intersection S to this is less than equal to this, right? And now this is less than equal to weight of S comma S bar, because little to more, right? So this is one inequality. I'm done. Okay, so one is easy. Okay, so this is done. Let's try to understand what other inequality could be slightly easier to understand.
S bar to that.
Huh?
The other with diagonal arc. The other diagonal arc.
This one.
Symmetric property.
Why, Sush?
Because S bar.
Exactly. So, okay, excellent. So now what can I write for this arc? Where it is? Which one it is? Fourth. No, it's third one. Okay. So let's try to understand this. Okay. So I can write it, what is this? Weight of O intersection S bar, O bar intersection S, right? O bar intersection S is less than, it is like O bar intersection S bar, O bar intersection S, right? So this is definitely less than equal to weight of O intersection S bar, comma, I can write this as O bar. No, S bar, S. Is it? Wait, yeah, this is fine, because O bar intersection S, maybe more edges. All right, look, when you increase a set here, it can only increase. And this is less than equal to weight of comma S, because O intersection S bar is contained inside S bar. So more edges, so more weight, because we are talking about positive, which is less than equal to weight of SS bar because of this. Okay, fine. So these two inequalities are easier to handle. Up until now, if you notice, I haven't used that this is a local optimum. Right? I have not used that this is a local optimum. So now there will be time where we will use that this is a local optimum solution to bound. So what edges we had handled? So we have handled this edges. Okay? So what we are not able to handle is this edges. What we are not able to handle at this point of time is this edges. Okay? Okay. So now what edges do I need to handle? What we have handled? Which cases we have handled? Let's pick up this one. Okay. First one we have not done. Okay. So we are interested in to understand what we want to understand. We want to understand how weight of O intersection S relates to O bar intersection S. This set of edges. Is that fine? Okay, this set of edges. Okay. Okay. These are internal S edges. Okay. So we have to just find the right set of vertices that will help us. Okay, just 1 second. Okay, so let's write down our why we were not able to do whatever we did. Okay, so what we know for all vertex, yes.
Given the local, the property of S from the algorithm, can't we say that is internal S edges?
That's what we have to prove.
But their weights cannot be more.
But that's exactly what we'll prove. That's all that we have to prove. But we have because there is not one kind. There are 4 kinds of edges. So we need to be a bit more careful. So let me write down. What can we say for all S in S? What is the local optima means? Okay. So here it is S, right? You could not move it out. Why couldn't you move it out? Because look at these set of arcs and look at these set of arcs, right? When I move here, I will lose the weight of this set of arcs and I will gain this set of arcs, right? Okay. So for all S in S, what can I write? I can write weight of S to S, S to S is less than equal to weight from S to S bar. Is that fine?
I think this is when you don't order should be different. Weight of small s to capital S it should be.
What?
In the first expression, because we are considering directed arcs, right?
Yes. So S to S. S to S.
Right. S is taken being small s is being
Yes,
taken out.
only this. So this is only not in neighbors to it, not out neighbors to this. Okay. So this, if I move, this will become out arc, and this out arc which is going to other people will go away. So this is what it is. Okay. 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 Let's try to understand what is this. Huh? What? We don't move it. This is one case we don't. There are other cases. So what can I get from here? Just give me a second. This should allow us from here. So now, what is O intersection S? Is this, right? Okay, excellent, excellent. Okay. Now look at this quantity. What is this quantity? Weight of O intersection S is O bar intersection S. What is this quantity? Look at this. Look at a vertex here, right? It is this. You understand? It is this, right? So what is O intersection to O bar intersection S? It is these kind of arcs, right? And now what I know about this, these vertices cannot move out. This set, look at these vertices here, look at this, these arcs are disjoint from, none of these vertices can move here, which implies this is less than equal to, what we can say, this is less than equal to weight of O bar intersection S to S bar. Is that fine? S to S bar. This is exactly what it says, no? That look at each of these vertices. Why I am not able to move to S to outside? Because this set of arc is less than whatever arc they are going here. And for each of these vertices, these arcs are disjoint, right? So their weight is here. So if you just sum this up, you can get probably here, right? But picturesquely, what happens here? Look at these vertices. What is this? Is that look at these vertices and look at these blue arcs. But for each of these blue vertices, what I know about them, hey, look at their arcs that are going this side, right? Weight of that is less than, weight of that is more than this, otherwise I would have made a move, which implies this. Is that fine? Okay. So what does this implies? What is O bar intersection S? I can write this as weight of S, comma S bar. No edge is going out. Is that fine? Okay. So now we have one more inequality that we could use. Okay. Okay. So this takes care of which one? This. Now what is left? I think this will be left. This red arc. Okay. So now let's write down what else do I know? For all t in S bar, why are we not able to move him to S plus V? Why? Why are we not moving something in t in S bar to here? Because if you look at, here is S and S bar, here is t. At this point of time, this is what is coming to him, which is contributing. And if you move him here, this is what will start to contribute. If I move t to s, what will contribute? This set of arcs. But I am not able to move, which implies for all t in s prime, weight of s to t, or rather let us say weight of t to s bar is less than equal to weight from s to t. Is that fine? Is that okay? Right? Why am I not able to move this vertex here? Because look at the out arcs that are going from t to s bar. Weight of that is less than equal to all the out arcs that are going from s to t. Otherwise, I would have made a move, local move. Okay? And this should allow us to contribute about this inequality. Let's see. What now we have to prove? Okay. So let's look at weight of O intersection S bar, and we have to understand what? O intersection S bar with O bar intersection F bar. Excellent. Okay. So now look at a vertex here. Look at a vertex here. This is some t, right? And now, okay, look at a vertex here, which is t. Okay. Now he has some arcs here, right? And he has some arcs here. Why are this t not able to move here? Because weight of these guys is less than whatever. No, like this. Okay. Okay. Weight to this is less than equal to weight of this, because when I move here, this will start contributing. But that does not happen. So what does this mean? But what is weight of O intersection S bar? Weight of O intersection S bar is this guy, and to what kind of arc we are talking about? This to this, right? So it means this to this for everybody is less than whatever this guy sends to this, right? So that is less than equal to weight of, right? Weight of comma O bar intersection S bar. Is that fine? Sorry. Yeah, this is exactly what it is. Is that fine? Look at what is this counting. O intersection S is here. Look at all the vertices here. Look at each vertex. This is what this is counting, right? Now look at this vertex. Look at the out arcs coming to T. Why did I not move T to this side? Because the weight of this guy is more, which is nothing but, look at, so what are these arcs? It is coming from S to all the vertices here, which is nothing but S to O intersection S bar. Look at the weight of arcs that are coming from S to O intersection S bar. That is more than this. Otherwise, I would have made a move to each other vertex. Okay. But now, what is this? This is less than equal to weight of S bar, and we are done. Okay. So this will give you 1/4 approximation. Okay. But let's just watch little bit and not we can be a bit more smarter here with the same analysis. So let's try to be a little bit more smarter. I will not. Okay. Let's just leave it here. Just leave it here. Okay. Just leave it here. Is that fine? Okay, I will not. Okay, is that fine? If I just leave it here, that's still hold. I mean, I just upper bounded by this. Okay, but now notice. Okay, this is fine. This is fine. Okay. Okay. So I use this here. I could have also used this is less than equal to weight of O intersection S. Is that fine? No, 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 no. Oh, right. This is exactly what I wrote here, right? So just leave it here. Leave it at 1 here. Okay. Now let's count what happens. Okay. I know that weight of OO bar, right, is less than equal to what we have. We have weight of O intersection S colon S bar. Is that fine? Is that okay? Plus weight of S bar from here. Okay, I got another here and another here I got weight of S O intersection S bar. Is that fine? Let's see what we can say from here. No, 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 I didn't write that. Look, you confused me. I wrote this is less than equal to O bar intersection S bar. This and this are not same. Okay, maybe. So this I can write it now. Okay, S O bar intersection S bar. Okay. Now let's look at this. What is this? If you put them together, what is this? It says S. Yes?
How did we write this first red thing which you just replaced?
Here, this one.
Yeah.
What is O intersection S? Is contained inside S, no? So if I allow S, I get more edges. So every edge in this set is contained inside this set.
Less than equal to. Okay.
This quantity is less than equal to. I'm not saying,
Yes.
yeah, I'm not saying it's at least. No. So otherwise I cannot write. Okay. So now why am I writing this? Because now if you look at S and look at S bar, what it says? All the what is this? What is S to S bar? What is this quantity means? If you notice, let me rub this. Okay. Then here it is. Okay. And this is my red. Okay. Okay. Now look at what is this first quantity telling us? S to O bar intersection S bar. S to O bar intersection S bar. So these are the edges that they are talking about. Is that right? Here. And what are these talking about? S to, right? So these are talking about these kind of edges, or so this quantity is talking about this, or yeah, right? This is the kind of arcs they are talking about. Is that fine? This quantity is talking about all the arcs that are going from here to here. And what is this talking about? All the arcs that start from S and goes to O intersection S bar. So these are basically all the black edges, right? But red and black edges is upper bound is exactly, this is equal to what? Weight of S bar plus weight of S bar plus weight of S bar. So what we get now? 1/3 approximation, right? So if I combine these two, then I get 1/3 approximation. Okay? Okay. So we got 1/3 approximation. But this also suffers from the same issue that it is not polynomial time algorithm. We can make some examples where we can show like weight, because every time weight will just increase by 1, right? So what should I do? Exactly. So we should just do, we shouldn't take minuscule escape, we should take giant steps. Okay. So what will we do for an algorithm? Okay. We will replace here, hey, don't do this, you fix some 1 plus epsilon, and you say, hey, I only make a possibility if my weight increases by some proportion. If my weight increases by some proportion, right? That's it. Right? Then you can show that then this will, what do you call, this may not give you a proper local optimum, it will give an approximate local optimum, but this will converge in polynomial time, some n log w or some, you understand? Because we will very quickly we will do this. But of course this will not give you one by, like it will not give you, but then it will give you what? Half minus little o of 1 approximation, 1 by third minus little of 1 approximation, because this epsilon is in your hand, right? You are losing little bit. So this is what I take giant step, right? So now rather than the moment, no, I only make a move if there is a significant increase in my cost, significant increase in going to that set, otherwise I don't make a move. Then this algorithm will converge in polynomial time, right? Because all you care about after this is what, right? Suppose, okay, why it will converge? Because now you fix your epsilon, right? And suppose max weight on edge is m, right? Then the cut edge is going to be some n square m. Maximum weight of the cut edge is going to be n square m, right? So you do 1 plus k, that it should be equal to n square m. 1 plus epsilon to the, so this is what? So k is like roughly log this, I think, something, okay, I don't remember, but like converge, okay. But then you lose a little bit, right? Because, but now notice I can fix epsilon equal to very, very small quantity, like 1 over epsilon equal 1 over n or 1 over n square, and only little bit in my approximation factor. Okay, so try to show that if this happens, then you can get such an approximation algorithm. Right? So this gave us a deterministic 1/3 approximation algorithm for directed cut. But of course, there exists a factor half approximation using randomization, but that I will not teach.
Okay, a week ago also you taught the generic submodular maximization. That also takes exponential amount of time, but it has 1/3 approximation.
No, it also takes polynomial time because you can also do the same heavyweight trick.
The first one that you had taught, it was like 2 power n and 1/3, and then the next improvement was the one where you have polynomial time, but you have a loss of 1/3 minus mod o of 1.
Little o of, not,
Little o.
okay, yes.
Little o of 1, right? So you are having similar performance here.
Yes, but
So then why break the black box and go into max cut and look into it?
just to give you an example of local search, and also to tell you that here it is very clear to show why we need to put S and S bar, right? And so probably people would have come up with this first and then would have gone there, say, hey, let me apply this idea of returning S and V minus S and then see what happens. It's just that the way I have organized the course is that I wanted to finish first greedy and then do, so I went to the depth of that, and then I've started local search. So that's it. More questions? Otherwise, I'm done for the day. Okay, then. Yes. We proved something very different. What did we prove? We proved, if you notice, is that the algorithm outputs a cut of weight, total weight divided by 2. But that has, so we use very weak upper bound on optimum, okay? But we can get closer to 0.84 approximation for max cut and both max try cut using semi-definite programming, which we will do later towards the end, right? We use, so this is more combinatorial result. There exists a cut, right, of weight at least total divided by 2. So that's the difference.